Okay, welcome everybody. We're going to get started in about a minute. Just waiting for people to get back out from the green room with the speaker. All right, Breese, let's make sure that you can still unmute.
All right, can you hear me now?
Yes, indeed. Excellent.
Excellent.
Okay, good. So we'll give it another 30 seconds and then I'll stop sharing the slideshow we have here for the pre-roll, and you can get your slides up while I'm doing the introduction, okay?
Great.
Great. All right, and since I know people are really interested in the meat of this presentation today, I'm going to go ahead and get the introduction started here so we can get to the main event. So welcome back everybody to the SMU Physics Department Speaker Series for Spring 2021. We've reached our penultimate speaker series event for this whole academic year. We're going to conclude today the April series and its theme of From Subatomic to Cosmic. And today's talk is also a perfect bridge into the final speaker series event, which is coming up a week from now on May 3rd. It's our spring colloquium, sort of a big capstone event. And the theme of that is going to be the unfinished standard model. Now, in a moment, I will introduce today's speaker, Professor Breese Quinn. But before we get started, I just wanted to make some of the usual reminders. So to our Zoom audience, to ask a question during or after the talk, just type the word speak in the chat window to indicate that you wish to speak. And we'll go ahead and we'll get you unmuted so you can ask your question in the order that things appear in the chat window. We use that as also to set up a question and answer queue at the end for people. So make sure you type the word speak in the chat window to get yourself in the order. This event is being recorded and simultaneously live streamed on YouTube. And we've currently got several viewers on YouTube. So welcome to the live stream. All right, so let me introduce today's speaker. So our speaker today is Professor Breese Quinn from the University of Mississippi. He received his PhD from the University of Chicago and joined Fermilab as a Letterman postdoctoral fellow in 2000. He earned a faculty position at the University of Mississippi in 2004, and there he is a professor in the Department of Physics and Astronomy and serves as the director of the University of Mississippi's Center for Multi-Messenger Astrophysics. He's been a member of several Fermilab experimental collaborations, including E791, KTEV, D0, and now Muon G-2. And on the Fermilab Muon G-2 experiment, his group has served in leadership roles in beam dynamics, and he himself serves as the CPT Lorentz invariance violation analysis group coordinator. On a personal note, Breese and I met many years ago when I was just a postdoctoral researcher and he was a newly minted faculty member. And we met because we were engaging together in high energy physics advocacy to the US Congress. So as members of the SLAC Users Organization and the Fermilab Users Executive Committee, he and I respectively had the pleasure of working together to speak on behalf of fundamental curiosity-driven science to elected members of Congress as well as members of the executive branch, which was all very scary. Breese continues that advocacy work to this day, and it's a pleasure to have him here to speak about one of what I think is one of the most exciting, fundamental, and curiosity-driven observations of our time. So without further ado, Breese, the floor is yours.
Hey, thanks a lot, Steve. So I've been doing that advocacy stuff for a long time. I think I've done about over 600 meetings with congressional offices by this point, did 50 of them this past year. So hopefully they'll still keep supporting this, and hopefully today's results will give them some motivation to do that as well. So thank you all very much for inviting me to bring to you the first results from our Muon G-2 experiment at Fermilab. We've been very excited about that this past month, and so yeah, we're very anxious to share those with folks. So you may have heard some news about this already. It has made the rounds in most of the papers and media all over the world, including Luke Skywalker. So we've been very excited about that. So what's the deal? What is this Muon G-2 and why is it so important? Well, just very quickly looking at the standard model of particle physics again. So this is the theory that we have for what are the fundamental building blocks in the universe, all the particles that are out there, and the different forces through which they interact with each other to form everything that we see around us, from the smallest scales up to the largest cosmic scales. Now, about the only ones that we ever have to deal with in our life are just the up, the down, quark, and the electron that make up all the atomic matter we know of, and the photon, which is everything we see. But there are a few others involved here, including the Higgs boson that we discovered several years ago. That was a big deal. And now the biggest deal, I think, since that time has to do with the muon. Now, muons are a particle that's very similar to the electron, basically just a heavy cousin of it. They have the same charge and the same quantum spin, but the two big key differences are they do have 200 times more mass than the electron, and consequently, they're unstable. They only have a 2.2 microsecond lifetime before they decay into smaller particles, namely these mysterious neutrino particles that are going to be very key for physics coming up in the future, and a positron or an electron, depending on the charge of the muon that decays. Now, this standard model has been incredibly successful over many, many, many decades. There's just an absolutely enormous number of phenomena that it has correctly predicted. In fact, just about everything that the standard model has anything to say about, it has correctly predicted for going on 50 plus years now. But we know it doesn't include everything. It has no prescription for dark matter, gravity, and a couple of other things. So we know there have to be things beyond the standard model. And and it has not been for lack of trying that we haven't found anything yet. We have looked all over the place in enormous numbers of channels, but so far basically come up empty. But does that mean that the standard model is perfect? Well, of course not. And the question is, are there really any cracks in it? Is there anything that it doesn't get right? Well, there are a handful of measurements that may disagree with the standard model, but nothing definitive yet. Two of the most compelling, interestingly enough, have to do with muons. One comes from the B decays measured at the LHC, looking at the ratio of different B decays to states involving muons and electrons. And basically, this ratio is testing lepton flavor universality, or in other words, do muons and electrons behave the same? Standard model says essentially they should, so this ratio should be 1. But they have measured a number different than that. Now, it's 3.1 sigma, which basically means something on the order of about a 1 in 1,000 chance that, that's just a statistical fluctuation. So it's not definitive, okay? But even more compelling than this one is measurements of muon G-2, which we're going to talk about today. In other words, do muons behave the way they're supposed to according to the standard model? And the last measurement we have on this is from a Brookhaven experiment about 20 years ago. And compared to the best theoretical calculations from the standard model that we have, there's a 3.7 sigma difference between the two. And so that's a lot more interesting. It's still not a definitive discovery of new physics, but it's getting closer. And so we want to check that out. So let's talk about that. Now, the magnetic moment for muon G-2, what's this about? Well, any particle with charge and spin will act like a tiny bar magnet with a magnetic moment. And this is, essentially analogous to you learn in basic physics. Anytime you get charge and move it, it produces a magnetic field. So you get some charge, spin it around, it's going to have a dipole magnetic field with a magnetic moment that is proportional to the spin of the particle and a G factor that sort of controls the strength of that interaction. Now, if you put such a particle in an external magnetic field, that field is going to exert a torque on the particle pulling on it, causing its spin axis to precess around the magnetic field direction, much like a spinning top in a gravitational field. It doesn't spin perfectly upright. It sort of does this wobbling around. That's its precession. Well, that's what charged particles do with spin in a magnetic field. Now, again, that G factor there affects how strong that interaction is, and thus how fast the spin precesses. Now, according to classical physics, you would expect that G factor to be identically equal to 1, but we're not dealing with classical physics here. We're dealing with quantum particles. And Dirac, looking at relativistic quantum mechanics back in the 1920s, calculated that a point-like particle should have a G factor identically equal to 2. And it stood that way for about 20 years until experiments finally found that there was a difference between two. It was actually a little bit larger than 2, about to a 1 part in 1,000. And so Julian Schwinger eventually found out why. He did the first quantum electrodynamic calculation that showed this difference. And so these two Feynman diagrams sort of show what's going on there. The first one is when you have a charged particle, in his case, the electron, interacting with a photon from the magnetic field. Just a simple interaction. And that would give you a G factor of 2, exactly. But Schwinger postulated that the electron could exchange a virtual photon. And this slightly more complicated diagram, if you include that in the calculation, accounts for this extra anomalous part of the G factor. So that's what he found. But what I want to emphasize here is going back to this number, what we're really interested in is not the G factor itself, but the anomalous part, the part that's different from 2. That's going to tell us about the more interesting physics. So we define an anomalous magnetic moment as A equal to G minus 2 over 2. And for Schwinger, that yielded a value for the anomalous magnetic moment for the electron of about 0.00116, which is the famous constant alpha over 2 pi. That constant, of course, is so important, it was engraved on his tombstone. I don't know if his wife really wanted that on hers, but it got there nonetheless. Now, since then, we have calculated this value to many higher orders in QED with incredibly high precision, to the point that the G factor for the electron is the most precise prediction ever confirmed by experiment in science. It's known to about 1/4 of a part per trillion, agreement with the standard model. Incredible feat. Well, if we know the electron so well, why are we talking about muons? Well, here's the thing. There's more to the story. Particles don't exist by themselves. They are constantly surrounded by a quantum foam of every other kind of virtual particle that exists, just popping in and out of existence. Now, these virtual particles that are forming this foam effectively sort of put this screen or shield around the particle, for example, the muon, that sort of shields or screens it from that magnetic field that's interacting with it. And sort of like the idea of you put your kid's drawing on the refrigerator with a magnet. Well, after they've drawn about 2 or 3 more and you try to stick those papers in there, it starts to shield it from the magnetic field and they eventually fall down. So it affects the interaction, putting stuff in between. Well, why is it the muon we care about? Well, for electrons, we know this so incredibly well. But the problem with electrons is that this anomalous part is almost completely just due to quantum electrodynamics. It's just the interactions of the electron with other electrons or photons. The weak interactions with other particles and hadronic interactions with other particles have a minuscule impact. In other words, we can't learn about much other physics with the electron. But for muons, it turns out that for all these kinds of interactions, the interaction is proportional to the square of the mass scales. So the muon has, about 200 times larger mass than the electron. So it's about 43,000 times more sensitive to other physics interactions. So the weak and hadronic processes will have bigger effects, and it makes the anomalous magnetic moment of the muon a very sensitive probe of new physics that we have not yet discovered. So that's why we want to look at muon G minus 2. Now, we can do a standard model calculation of a mu, just like we did with AE. The quantum electrodynamics is relatively easy to calculate, and we can calculate it with very high precision to about 1 part per billion. Electroweak interactions, those with the Z and W bosons, that can be calculated in the same type of way with perturbative quantum physics. And it's a much, much smaller effect, but it's got also a very small uncertainty, still only about 10 parts per billion. The really tough part comes in when you're dealing with hadronic interactions, with quantum chromodynamics. This strong force interaction, these are really hard to calculate. You cannot use very straightforward perturbative algorithms for this, and you have to do much more complicated and difficult calculations. Very tough to carry out. And you'll see that there are two classes, what's called hadronic vacuum polarization that sort of looks the same as some of the others, but it has a much larger impact on mu than electroweak does, but the uncertainty is lots higher. And the hadronic light by light components are somewhat smaller in effect, but also have a very high uncertainty relative. So these are the ones that are really important for determining what our expectation is from the standard model. Now, there is a Muon G-2 theory initiative, a group of over 100 theorists that are working just on this problem. And they have come up with a white paper last year that the consensus view of doing all these calculations and adding them up comes to a total standard model value that you see in this next to bottom line. When you compare that theory with that Brookhaven experiment result, there's a difference. A small difference, 279 parts per billion, but our uncertainty on it is 279 on the last three digits, but our uncertainty on there is that 3.7 sigma difference that I mentioned. So what is causing that excess? Well, it may be new physics. And so it could be supersymmetry, it could be dark matter, it could be any number of other things, but we want to find out, you know, what monsters are lurking in that little circle there that we don't quite know about yet. So the only way to know these things for sure is to get the uncertainties down even more to push that 3.7 up to that 5 sigma discovery level. So we need a new experiment. So here's that new experiment, the Fermilab Muon G-2. Now, the idea for this one is to basically rebuild the Brookhaven experiment at Fermilab, but do it better, stronger, faster than before. Well, not faster. It's taken us a long time to get this result out. But still, just like with Steve Austin, we are going to start building with the original core foundation. And in this case, it's the Brookhaven storage ring, the magnet that we put these muons into. We need to pick that up and move it to Fermilab, where we can use Fermilab's more intense, cleaner beams to get 20 times more data to improve the statistics. And also, in the meantime, we'll improve everything in the experiment, the detectors, the algorithms, the way we control the beam, all of that, to eventually get a 4 times reduction in uncertainty, getting down to 140 parts per billion measure. Here's our collaboration. Over 200 of us from about 3 dozen institutes across about 7 nations. And what's really great about this collaboration is it includes people from particle, nuclear, atomic, optical, accelerator theory, an incredibly diverse group that we've put together. It includes some of the great vets from the BNL experiment and lots of new, fantastic, young, and some somewhat old talent to add in there. So, here was our big move. We picked the magnet up, and this was it in Brookhaven on the upper right. The really important part were the superconducting coils inside. That had to be moved in one piece, and it could not flex by more than 1/10 of an inch anywhere in the move. So we put it on a barge, sailed it down the sea, went up the rivers. This is me and my kids at the lock on the Tenn-Tom waterway, just about an hour from our house. And yes, that little girl is now going to college next semester. And so it's been a while here on this journey. Scary. Put it on the truck on the tollways, eventually got it to the thronging crowds, you know, our adoring fans at Fermilab. 3,200 miles, 3 months, but it got there in one piece. Then we put it back together. So we put the coil down in there. My team from Ole Miss was very instrumental at getting the storage ring vacuum chambers inserted into the magnet. And then here it is. This is the main idea, all put together. So here's our ring at MC1 at Fermilab. And the idea is to put muons in here and spin them around a magnetic field. And their spins are going to precess like that top as they go around. And that is what is going to give us information on the anomalous magnetic moment. But the question is, how do you observe that? How do you observe this spinning precession? How do you measure it? There are 4 key principles to doing this kind of storage ring muon G-2 experiment that this depends on. The first, muon, when you take a primary proton beam, which we have at Fermilab, we speed them up and slam them into a target. Pions are some of the particles that come out of that target, along with a lot of other stuff. But when those pions decay, the forward decay of those pions produces a polarized muon beam, 97% polarized. So we've almost got a pure polarized muon beam, and that's really important that we know where those spins are lined up. Okay, the next part, the second thing, is that the anomalous magnetic moment that we're trying to measure is roughly proportional to what we call the anomalous precession frequency, okay? And so what I mean by that, there are 2 frequencies that have to do with the muon's motion going around. One is just simply the frequency that it goes around the ring. You know, what is the frequency that it makes a circuit? That's called the cyclotron frequency. And essentially, it's how fast the momentum vector precesses, comes all the way back around, okay? And then there's the spin precession frequency. Now the spin, if G was equal to 2, exactly 2, like Dirac thought, then as the muon went around the ring, the spin would stay locked together with the momentum. It would never vary from the momentum. And so nothing would ever happen really. But if G is bigger than 2, then the spin vector is going to precess faster than the cyclotron vector will. And so what we do is we subtract the cyclotron frequency from the spin precession frequency, and that gives us the anomalous precession frequency, how much the spin is precessing relative to the momentum. And that anomaly, that extra bit, is what we're interested in. So the third key principle. Now, we put these muons into a horizontal storage ring. And so the idea is that it's basically going to be horizontal motion around this ring. But it's not perfect horizontal motion. There is some vertical beam motion going up and down. So we have to employ electric quadrupole fields to focus the beam vertically, to keep it contained vertically. The magnetic field that we establish with our big magnets, that focuses them horizontally. But we've got to have these electric quadrupole fields. But when we put an electric field in there, it complicates our simple omega A equation. Remember what I just showed you was just this simple term that has a direct proportionality between the precession frequency and the anomalous magnetic moment. But when you have some vertical motion, then this term is non-zero. So that gets more complicated, right? My momentum is not perpendicular to my field. Not totally. But then when I have to put an electric field in to contain that, well, I get this third term and it gets really nasty. But the magic here is that if you run at just the right momentum at a gamma factor of 29.3, this term cancels out. And that's what we call the magic momentum of 3.09 GeV. Then we cancel the last term. But our beam is not perfectly planar, and the muon's momenta are not a delta function right at the magic momentum. There's some spread. And so we're going to have pitch and E field corrections to our omega A measurement. And we'll get to those later. Fourth principle, muons eventually decay to positrons, as I showed you earlier. Well, this decay is self-analyzing due to parity violation. The highest energy decay positrons will be preferentially emitted in the direction of the muon spin. So we want to know where the spin is pointing all the time. That's what we're all about here. And the way we get access to that spin is by seeing where the high energy positrons are coming out. And so by counting our rate of high energy positrons, we get information of when the spin of the muons is pointed in the direction of our detectors. And so look at this little animation I have. I'm going to rotate the spin relative to the momentum, precess it. And here's the energy of my positrons, an energy spectrum. And then I have some threshold. I'm only going to look at the high energy ones. And you'll see how the number of high energy positrons goes up and down depending on what the alignment of the spin and momentum is. So let's look at that. So you see it changing here. And as the spin gets lined up with the momentum, you get a high rate. You're at a maximum rate of high energy positrons. But then when it's anti-aligned, you're down at a low rate of high energy positrons. And so this produces what we call our wiggle plot. And the period and thus frequency of this wiggle is our anomalous precession frequency. So that's how we're going to get at our physics. Okay, so here is our basic equation that we're looking at to get this anomalous magnetic moment. Now, there are two things we have to measure. One is the anomalous precession frequency. We get this from that wiggle plot. And then we're going to have to measure our magnetic field to very, very, very high precision as well. And you may have heard in particle physics that we're only supposed to measure frequencies. And that's because in general, we have the ability to measure frequencies at much higher precision than anything else, like momentum or energy or anything like that. And so we work out a way to measure our magnetic field in terms of frequency, in terms of the proton-Larmor precession frequency. And so there's a simple relationship between the proton precession frequency and the magnetic field. And we use nuclear magnetic resonance techniques to do this, to relate the two. Now, you also have all these constants that come in, but all of these constant ratios are known to on order of 10 parts per billion. And so this is what we get from co-data from other experimental measurements, and these two things are what we have to measure in our experiment. So that's the game plan. So we have to start with the beam. So we go to Fermilab, we get a 8 GeV proton beam, put it into a ring, get it up to 8 GeV, and then we divide it into 4 bunches that are about 150 nanoseconds wide. And those proton bunches we extract one at a time to hit our target, from which we produce the pions that I showed earlier, which then decay into muons. And so about 80% of them decay along this short transfer line. And then we use magnets to select our magic momentum muons. Then we put those into a delivery ring, spin them around about 4 times to clean up the beam. All the remaining pions decay by that point. Any protons left in the beam are separated out just due to the mass difference. They're slower, okay? And so then we can kick them out of the beam and just send a pure polarized muon beam into our storage ring. So here's our beam. Now we're ready to put it into our ring. First thing, we got to have that magnetic field ready to accept it. It's about 1.5 Tesla. 12 big iron yokes, C-shaped yokes, excited by those superconducting coils that I showed earlier. 24 iron top hats, 72 pole pieces, 864 wedges, 8,000 super thin iron foil laminations with edge shims and active surface coils to shape the field at an incredibly high precision to get it very uniform. And so to give you an idea of how we've done that and did that work, the blue line here shows you the field uniformity at Brookhaven. Now, after we reconstructed this at Fermilab and first put it together, this is what it looked like in the red. We got a lot of work to do to get all these thousands of pieces in to shape our field. And so I'll play you an animation that represents work over almost a year of shaping this field. And so you'll see the field uniformity throughout the circumference of the ring start to move around as we add different components into that magnetic structure. And then as we start to move just a few months from, you'll see it shift down. And now we're going to start moving into the sort of the fine tuning of it with all those little foil laminations and such. And so now sort of section by section, you'll see it sort of come up into a more uniform position. And now we're in the final months, and then it comes out to a uniformity 3 times better than we had at Brookhaven. So we're well on our way to getting to that smaller uncertainty level. Okay, now we've got a magnetic field. So we got to get our beam in here now. So we've got to inject it. This little picture shows you the quadrupoles that the muons see as they're coming into our experimental hall, looking down the beam pipe. But now we've got to get them into the storage ring. But the problem is, how do you get these charged particles into a huge magnetic field ring? Well, you need a field-free region to inject them. So we have to use this very special inflector magnet with about a 9-millimeter beam channel in it to thread the muons through in a field-free region. But this thing can't disturb the big overall magnetic field. So it's got a superconducting sheath around it to prevent any disturbance. And it's a real tour de force designing this thing. And it puts the beam in, but it's only able, it can't get it right on the ideal orbit. It ends up getting it in about 77 millimeters off center. So we've got to get it on the right centering for the orbit. And we do that with kicker magnets. We need to kick the beam onto the stable orbit. And we do that with these conducting plates. And we have a huge high voltage pulse on these plates that provides a 10 millirad kick to get it onto the stable orbit. Now, there was a challenge for this in run one. Now, one thing is you've got to do this in less than 149 nanoseconds, because that's how long it takes the muons to get around the ring at 3 GeV. And so all of your kicking of that magnet has to be over and done with after 149 nanoseconds. So you can see this black line is the length of our kicker pulse. The dotted line inside is the width of our bunch of muons that comes in. There is some ringing in the kicker, but that ends up being okay because that's done by the time we start taking data at about 30 microseconds. Now, there was a challenge in run one, one of the biggest challenges we had, and that was our kicker was sparking. It was sparking due to some components, and that limited the high voltage range that we could operate this at. We couldn't quite get up to the high voltage we needed to get it right in the center. And so our beam was off center for run one. We fixed that in run two and on. But that is an issue for this data that I'll show today. Then once we got the muons in here, we've got to keep them focused, right? Those electrostatic quadrupoles to focus them vertically. It's done in 4 sections of these quad plates, plus and positive on the top, negative on the side. So it will tend to push our positive muons towards the center, but the magnetic field ends up keeping them contained horizontally. These sections cover about 43% of the ring circumference. Here are a bunch of the Ole Miss folks that are where this was a big part of our contribution to the experiment. Juan Wei aligning and installing the quads, Jason here and Meghna that are teaching us how to use them, and Meghna and Sudeshna that were performing upgrades to make them operate better with 100% uptime. There was a big challenge here as well for run one. The RC time constant is designed to fully charge in 5 microseconds. But 2 of the high voltage resistors out of 32 were damaged for run one. And the charging time was 100 microseconds for these, extending well into our data taking period. And that really caused an issue that took a while for us to understand and had some real things that we had to deal with that I'll explain later. But keep that in mind. Again, this is something we fixed for run two though. All right. So we all want to know where our beam is, and we do that with straw trackers. We've got 2 stations of straw trackers off to the side. They're, just to the right of our storage area. And they're 8 modules, 128 straws each, and we use those to reconstruct the path of our decay positrons. And so we can point back to the point that they decayed from, where that muon decayed. And we use that as basically tomography to know where our beam is. And so this, you can see that our beam is sort of swimming left to right. It also swims a little bit up and down, and it also breathes in and out. The width of it changes a little bit, this beam motion. And so we know that from these trackers. But we want to measure the positrons, right? And so we use calorimeters to do that. We have 24 calorimeter stations around the ring. Each of them has a 9x6 array of lead fluoride crystals to measure the arrival time and energy of the decay positrons. Obviously, we need the energy to know if it's a high energy positron that's correlated with the spin or not. But we also need to know the time that it hit because we're measuring frequencies. It's all about the time. And so we've got to get both of those things. And so going back, I'll show you, you can see the data building up fill by fill by fill of muons over an hour run, and the statistics building up and building up. And so this is us collecting those high energy positrons, and this oscillation you see is the anomalous precession frequency that we want to fit for and extract. So let's take a ride through the beamline. So I'm going to show you what it looks like to go as a muon, to go through our storage ring, first with a computer simulation, and then actual video footage of going through the ring. So you'll see various things in here. We're going through the quads. At some, whoop, there are straw chambers off to the right. This wall back here is a calorimeter just on the other side of that vacuum wall. And now we're going through more quads, and if you look carefully, you can probably find the kickers in there somewhere. They're a little bit hard to spot, but you see all those elements that you go through. And now this is from a camera that we put inside to see what it actually looks like. So here again are the straw chambers that off to your right, and just behind them is on the other side of this wall is one of the calorimeter stations. And now coming up ahead is one of our quadrupoles, electrostatic quadrupoles, top, bottom, left, and right, inner, outer, side plates. So that's what our storage ring looks like inside. That's what our muons go through. All right. So back again to what we're measuring. Again, all these constants we get from the particle data book. Omega A and omega P are what we're measuring. This is the precession frequency. This is the magnetic field. So the numerator, that's our wiggle plot. We're extracting the frequency of that. The denominator, we've got to do a very high precision measurement mapping of our magnetic field inside the storage region, and then convolute that with our beam distribution, because it's important to know what the magnetic field is, where our muons are. And so we put those things together for the denominator. It's not quite that simple. There are a lot of corrections we need to make for various detector and beam related effects. We've got to do some calibrations as well, factors to play into it. And so we're going to look at all of these individual parts step by step very quickly. First, the big important one there is omega A. What is the frequency that we see in the wiggle plot? So we've got to measure that. So the wiggle plot is we're getting a fit to the exponential decay of the muons because they're decaying, right? And so as time goes by, we get fewer and fewer of them. So there's an exponential decay and the anomalous precession rotation, oscillation. And so those two things we're fitting for. You can do it with a simple 5-parameter fit. N, the first one, is just how many muons got stuck in the ring to begin with. And then tau is the lifetime of the muon in the ring, which is about 64 microseconds at our boost. Then A is the asymmetry or amplitude of our oscillation. And then omega A is the frequency that we're trying to find. And then phi naught is just the phase that they come into the ring with. Physically, it's unimportant for us, but it's part of the fit. Now, we do the simple 5-parameter fit, and you can see it doesn't look very good, does it? You see that we've got a bad chi-squared for the fit, and you can see obviously there's still some oscillation effects going on. So there's stuff we've missed. There's some beam effects going on that we have not accounted for in our fit. And in a Fourier transform of this, you can see them very clearly. What most of these have to do with is different beam effects. The biggest one being what's called coherent betatron oscillation. And what that essentially means is, in this little cartoon at the bottom, these different vertical lines show you the cyclotron wavelength, basically how many times you go around the ring. And then the blue line is basically the wavelength of the radial swimming in and out of our beam. And they do not match each other. And so what's going to happen is you're going to have some interference between these, and muons at a given detector, when you come around to a given calorimeter detector, they will be sampling them at different phases in this radial motion. And so we've got to account for that we're not seeing them coming from the same places all the time. That's the coherent betatron oscillation. And we see spikes in that that's responsible for a lot of this disagreement. Plus, we have things like muon losses, and actually the arrow's pointing to the wrong place. The muon losses and pileup are this thing at zero frequency. It's this slow effect. So we've got to take those things into account. Now, so here's our CBO, this swimming and breathing of the beam, modulating our spectrum. Then there's pileup, and that's when you have too low energy that we don't want hitting our calorimeter at the same time and faking a high energy positron. So those get into our wiggle plot when we don't want them to. And so we have to figure out how to subtract those out. Then there's muon loss. And muon loss is not all of our muons are at that magic momentum. Some are higher, some are lower. And if they're too far out of the spread, they don't stay in. They tend to get pitched in or out. And so we can measure those by looking at coincidences among 3 calorimeters. Because if a muon gets out, it's not going to get stopped in a calorimeter. It's a minimum ionizing particle. It goes straight through. And so if we get a triple coincidence with 3 calorimeters at minimum ionizing energies, we know that's a lost muon. We can count those, subtract them out. With pileup, we can get our original sort of double humped energy spectrum. And then we can use different algorithms to look in a sort of shadow window at a different time than when our muons are there, and remove out the pileup spectrum to get this blue. I think I'm a little bit colorblind, but this spectrum here that is just our high energy positrons. So we get those into our fit. And now it's not 5, it's more like a 21 or 22 parameter fit. But when we get all of those, and it's a lot of parameters, but I want to emphasize that all of them correspond to real physics. They're not just empirical, get it in to make the thing fit. And you put those all in and we get very good agreement in our fit. All the residuals go away. And this is a very high quality fit that's ready to go into averaging to come up with our omega A number. So this is how we pull omega A out. Now, we do consistency checks. It should not, the value for omega A that we get out shouldn't depend exactly on when we start fitting in that data. Back here, we're starting at about 30 microseconds, okay, after the beginning. And these wiggle plots, by the way, it's sort of folding back on itself, going out to 100, then 100 to 200, then so on and so on, over about 700 microseconds, 10 lifetimes that we're doing this. So we start at about 30 microseconds. But if we start at 40, 50, 60, we still should get the same value. And it is consistent, so that checks. We should get the same value if we use 1 calorimeter or all 24. And so that checks out as well. And then also we've divided our data into 4 separate data subsets, and we get the same value for all of them. And also, we do multiple independent analyses to extract omega A. We have 6 different independent teams doing a mix of 2 different clustering algorithms in the calculator, 4 different analysis methods, 3 different algorithms for removing pileup, and the 4 different data subsets. All of it and many other consistency checks agree. And so we come out with about a 400 part per billion statistical uncertainty on our omega A extraction, with about a 50 part per billion systematic uncertainty. But that's not it. There are corrections that we have to do. Remember that pitch and E field correction I mentioned due to the fact that we don't have perfectly horizontal motion. Well, for the pitch, we do a correction based on the average vertical angle of our muons. And it's related to the equilibrium radius for the ideal orbit and the amplitude of this vertical motion. It's got about a 200 part per billion correction, but we know it very well to about 10 parts per billion. The E field correction, because not all our momentums are right at gamma 29.3, this correction is proportional to basically the positioning of our beam. But remember, our beam was off center, and that was a little bit of an issue for us. So we have a fairly large correction due to this, but the uncertainty on it is about 50 part per billion. Again, not huge. In run 3, our kicker was fixed to get the beam centered. So this correction is much, much smaller in later runs. Then there's this muon loss correction. Now we pulled out a lot of muons, but there's this more subtle effect due to our muon loss. And that is, what if that phi parameter that I mentioned in the fit was not a constant? What if that phi is time dependent? Well, then that's a huge complication. It can be time dependent because of these lost muons. Remember, they're at a different momentum, right? They have a different phase coming in. Now, the phase that we fit is just an ensemble for the whole distribution, but the lost muons are in a different part of that distribution than the ones that stay in the beam. And so as we lose those, it shifts our distribution of muons, our momentum distribution. And so it shifts the ensemble phase. And so the phase that you would fit for early and late parts in the data will be different. So it's time dependent. And if you work through the expansion of that, what that ends up doing is adding an offset, a bias to the time-dependent, part of the oscillation. And so we extract an omega A prime that's not the omega A of the actual spin precession. So we've got to understand that. We do it by measuring the phase as a function of the momentum and putting that with the change of the momentum relative to time from our muon loss. And so it turns out that this is a very subtle problem, but it's a almost insignificant effect, but we had to check out to make sure. This is the hard one. This is the one that took us about 1.5 years or so to figure out, the phase acceptance correction. Now, this is where I sort of get into the weeds, so bear with me for one slide. Our detector acceptance, which essentially is which positrons from the beam can we detect with our detectors based on where they come from. It depends on the muon decay position. And that muon decay position couples to the phase. Here is a plot of decay y versus x, so just a position of our muons, and then how that couples to phase. So you get a lower phase in position 1 than you do in 2. Now, that means that muons at position 1 and 2 will have different phases, and thus, where their peaks occur in the wiggle plot will be at slightly different positions. That is fine if your distribution is staying stable because we're fitting for a whole ensemble. But the problem is our distribution is not stable. Our beam was unstable because of those damaged quadrupole resistors that I mentioned before. They weren't charging in the 5 microseconds. They were changing well into our fit time. And so basically our vertical distribution was getting squeezed during our fit time. And so you see that happening here well past 30 microseconds. And so what's happening is our late beam is sampling a much narrow range of phases than our early beam was. Now you put those two effects together, and now what happens is you've got the change in phase relative to position together with the change in position distribution relative to time, and that gives you a time varying phase. And you can see this big effect over this several, up to 100 microseconds. And that took a long time for us to suss out. Has a significant offset, which is fine, but it's got a pretty big uncertainty on it, 75 parts per billion. Again, it's been fixed in run 2, so that correction is going to be much smaller. That's it for omega A. Okay, the denominator, the magnetic field. 2 things here. I've got omega prime tilde. What's the prime and tilde to do with? Well, the prime has to do that we're doing this with proton NMR, probing it with nuclear magnetic resonance. And the prime has to do that we're calibrating this in terms of the proton frequency, precession frequency, but doing it in a proton shielded in a spherical sample of water. So going from just the proton precession itself to this spherical water sample, you get the prime. There's some correction factors in there. And then the tilde is the fact that we're not just doing it for one little proton. We've got to do it. We've got to fold this in with the muon distribution around the ring and throughout the run. So it's putting those things together. So that's what all those little symbol parts are. With that together, how do we do it? We've got almost 400 fixed NMR probes above and below the storage region, sort of outside the vacuum storage region, that monitor 24/7 the magnetic field. But the muons aren't outside the storage region, they're inside. And there's metal stuff in between, so you don't measure exactly the field that the muons are seeing. So you do that, we do it with a very special magnetic NMR trolley that has 17 probes in it, that once every 3 days, we just run this trolley around the ring slowly, measuring 2D slices of the magnetic field at about 8,000 positions around. And so we've got these very accurate points of the magnetic measurement, you know, at these points about 3 days separated. And then we've got the fixed NMR probes in between, but those can sort of drift a little bit. And then those get corrected, you know, sort of through interpolation, pull those back and corrected to tie to the trolley values. And this gets us a very, very good measurement of our magnetic field. It has to be calibrated to the absolute calibration to water and helium-3 standard samples that we do at a very special MRI magnet at Argonne. And then it has to be folded in with the muon distribution that we get from the straw trackers to get the magnetic field distribution that our muons actually see. And our uncertainty on that is about 50 parts per billion. We've done quite a good job with that. 2 corrections with the magnetic field. One is kicker transients. We slam these plates with a very high voltage pulse, 280 Gauss that we're getting out of this. It creates a 150 nanosecond transient field that produces eddy currents in the conductors. And those eddy currents are moving charge. They create magnetic fields that perturb the magnetic field that we just measured when we didn't have muons in there. And so we had to, it's really hard to measure. The fixed probes have walls between it. The kicker is off during trolley runs, so you're not measuring the effect. And so we had to design a special Faraday magnetometer to measure rotation of polarized light in a crystal, okay? And so this is one of our postdocs, Alex, installing the magnetometer. And we did that, and we came up with about a 30 part per billion correction with about a 30 part per billion uncertainty on it as well. So we did handle this, but it was sort of tough to nail down. This was worse, the quad transients. When we pulse the quads, really super high voltages, it makes those top and bottom and side plates vibrate, mechanical vibrations. But that, again, is going to perturb the magnetic field, moving conductors in the field. And so that was mapped with some specially built NMR probes as well. It's done over 8 bunch sequences, and you see there are huge magnetic field variations, about 400 parts per billion. But it's not that bad because we only care about what's happening during these gray slices. That's when the muons are actually in the ring. And if you measure this over the period that the muons are in the ring, across the whole ring, and average over that, then it's a fairly small shift actually. But we have a very large uncertainty on it for run 1, but that's simply because at the time we did not have time to get a complete map of all the quads. We have before run 2, so this uncertainty is much, much smaller on our data moving from run 2 onward. That was a really, really tough thing that took a long time to nail down. Here's all our corrections and uncertainties. So we've gone through all of them that I've just talked to you with, and now we're ready to unblind, right? We've uncovered everything, we're ready to get our thing, but there's actually something that we haven't addressed yet. The clock. The clock correction. Remember, this is a blinded analysis, okay? We didn't know the answer beforehand while we were doing the measurement. And the clock is what has to do with that. Both our omega A and omega P frequencies are measured by a clock. Frequencies have to be measured by a clock. We've got a GPS antenna on the roof, goes to this receiver, and it's, you know, that's like a part per trillion clock measurement. And then that gets sent to our field and precession clocks that are separate. And the precession one in particular is hardware blinded or detuned over a range of about 25 parts per million. And we're trying to make, 100 part per billion measurements. So this is a huge offset, hardware offset that we put in that we don't know. Only 2 individuals in the world know this. 2 of our friends from the Fermilab Directorate that we trust with our lives. They check that clock hardware offset weekly. Each run is separately blinded. When we were ready to go, we all agreed that we want to unblind. Those secret sealed envelopes were held at Washington and Fermilab, and they were delivered to us for a vote on opening on February 25th. So we got everybody together on Zoom, took a vote, unanimous, everybody's ready to unblind, and here it is.
Put it up on the screen.
Put it in the chat. Wait, 399.
3999 7844. Same number. Yay. Yep.
So it checks out. We're ready to go now.
And this is what we get.
Oh, wow. Wow.
We confirm 821.
All right, we confirmed 821. So we did, in fact, the Brookhaven measurement, the one from 20 years ago. We've done a lot of analysis. We've checked a lot of things over those 20 years. All of that 20 years, this current analysis found no issues with the Brookhaven result that would require any kind of changes to what they did. As far as we can tell, they did things just right. Our measurement on our run 1 measurement that we're presenting today, based on about 6% of our data, is consistent with Brookhaven, 15% smaller uncertainty. Because they are consistent with each other, we're ready to combine those, and together the experimental average has an uncertainty of 370 parts per billion. That is comparable with the theory uncertainty of 350 for the measurement. It's comparable with the 370 part per billion theory uncertainty. And now the tension with the standard model stands at 4.2 sigma. So we are getting tantalizingly close to really nailing down on just 6% of our data. So we're very excited about this result. 4 publications across 4 journals, first time ever that this has happened for one result. And again, showing the diversity of what goes into this experiment. That's in the accelerator and beams, it's in atomic physics, it's in particle physics, and it's in phys rev letters, all published together. How close are we to our goals? Well, this is about a 460 part per billion uncertainty, and we're shooting for 140, this right-hand dotted line. You can see that our uncertainty is completely dominated at this point by statistics. And so we're gathering much more statistics, and we're well on our way to hitting the value that we need for that of 100 parts per billion. Now, the uncertainty, we want to get down to about 100 parts per billion as well. But you can see those 2 that I mentioned that were big issues, right? The quad transients for the denominator, the phase acceptance for the numerator that are already, each individual is above what we need, okay? But those, we've got really good tracks for making them much smaller. So we're well on our way to getting to this goal in systematics as well. And so we think we're in good shape. What's next? Well, this is our result on 6% of the early data. Run 2 and 3 are in the can. We're currently analyzing that. Hope to publish that result in about 18 months, reducing the overall uncertainty by about a factor of 2. Run 4, we're currently about halfway through. Then we'll do more data collection in run 5 next fiscal year, aiming for another reduction in it by a factor of 2. So we think we're going to get down to there. And I want to give a big thanks to particular all the folks in my Ole Miss group that have worked on different parts here and that you saw pictures of along the way. And so thank them in particular, as well as thanking all of you for giving me the chance to bend your ear for about an hour here. And to a few particular examples from my collaborators that I've drawn heavily on their slides from, it takes a village. So, so thanks to everybody. I really appreciate this opportunity.
All right, no, thank you very much, Breese. And let's give you some proper applause here at the end. Since Zoom is so bad at doing applause. All right, this is the time for questions. So, oh, Tom looks like he has a question. Let me get you unmuted here. All right, Tom, keep yourself unmuted until you're satisfied with the answer. Go ahead, Tom.
So this is a great result and a great plug for precision physics. Question I have is, you must be able to measure the rest frame lifetime of the muon very well. When you do that, I'm sure you guys have done that.
Mhm.
How well do you do, and does that value change very much as a function of time from injection? And then finally, the third question, if I can squeak one in here, does that tell you anything interesting about your systematic effects?
Well, yeah, that goes back to, my the first simple 5-parameter fit. If I can get to that. Yeah. So yeah, basically that's part of the fit result that we get is the lifetime. And let me see. I can't remember. I can't remember what the uncertainty we have on that. It's very good. I mean, it's not like it's so good that it's competitive for actually determining the lifetime of the muon. But it's one of the things that we checked. For example, as we varied our start time, right? That was one of our consistency checks. And let me skip down to show a little bit more of that. Yeah, so here are lots of the different things that we did consistency checks with. And let me see, doesn't have everything in here, but it was one of the things that we did that was related to the start times, for example, is, as we vary that start time, are we getting, a consistent lifetime measurement as well, since that's something that, we can pin to an actual known quantity. And it doesn't vary. It's one of the things that we're checked, and it's right on. But I can't remember exactly what the uncertainty on it is. It doesn't add anything to our knowledge of the lifetime.
Okay, great. Thanks.
Yeah.
All right. Other questions? Remember, type the word "speak" in the chat window if you want to go ahead and ask a question, and we'll get you unmuted. While we're waiting for somebody else to jump in here, I'm gonna jump in with my prerogative and ask you a question, Breese. Sorry to make you jump around on the slide deck. Can we go back to slide 32? There was something on there that I don't think you called out, and I'm just kind of curious about.
Yeah.
I suspect it has to do with internal cross checks in your experiment. So you had shown this plot where you broke the data down into 1A, B, C, and D.
Yeah.
Okay, so what's the horizontal axis on that right-hand plot?
Yeah, the horizontal axis. What that is you see these C, W, E's. That's like Cornell, Washington, Europa, Shanghai. Those are Boston. Those are the different 6 teams. And the T, A, R, and Q, that's the T method, a symmetry-weighted method, ratio method, and Q method, the 4 different analysis methods. So you're looking at 3 different consistency axes here, basically: the data sets, the teams, and the analysis methods.
Yeah. So basically, you have sort of independent methods even within the collaboration, and
yeah,
it's a good way to find like potential mistakes or inconsistencies. But in this case, there's just, even though they're all doing something slightly different, there's pretty striking agreement between.
Yes. Now it is true that all of these are highly correlated. They're highly correlated. They're all looking at the same data, and some of the methods are more similar than others. But there is a lot of different choices in what pilot method you used for a T method versus an A method and all this. And so anyway, yeah, all of that's involved. So it was a really good consistency check. And by the way, there were actually 2 stages to our blinding. There was the overall blinding, with the secret lock cabinet and everything and envelopes. But there was also a relative unblinding among different analyses. And at some point, several months ago, we removed the relative unblinding to check how consistent all of the different analyses were to each other. And that's essentially what you see here. It was essentially this plot almost not changed at all from this final plot. Everything lined up to this agreement when we did the relative unblinding. So that gave us enormous confidence to move ahead with unblinding the full result. The only thing that held us up there is we were still trying to nail down this phase acceptance. That was the big thing that took a few extra months to convince ourselves that we understood that well.
So Carl has a simple question. He says the electron detectors are inside the ring because the electron has a lower mass and bend more than the muons. Is that right? Or what's the reason for having them inside the ring radius?
Oh, well, but you can't have them within the storage ring because it would be destructive to our muon beam. And so we've got to, take everything out. For example, we also have some beam monitors, these beam monitors that come in that help us image our beam as well, but they're destructive if we put them in there. So we don't have them during data taking. And so the detectors all have to be outside of the storage region.
Right.
Okay, so you just got to pick somewhere to put them and consistent. You could put them outside the ring, but it's engineering and it's just a lot simpler to do it inside. And so
it has nothing to do with the fact that like the electrons would preferentially bend.
Yeah. You could do them out there, but you wouldn't get nearly as much data.
Okay.
Because when the electrons are emitted, it's from a decay. They're lower energy than the muons. And so they're lower energy particles in this magnetic field. So they're going to tend to, spiral into the ring instead of out.
Okay.
And so, that's how we can get, the highest, rate of our positrons. You wouldn't get much data if you were looking somewhere else out in the ring.
Yeah.
And so, that's, what we're looking at tends to spiral in. And so, so that's why they're there. But we want them, as close to that storage region as we can, just right up against it, to get the maximum data from the, since they are boosted up there.
Cool. All right. I don't see any other questions, but I think there's one more that I think that certainly people who've been talking about this result have brought this up. And yeah. You're clearly a hardcore experimentalist, right? You are deep in the weeds of the experimental part of this. And I think you've done an excellent job of convincing an audience here that this is a really methodical, dissection of this experiment to make sure that no correction is left unmeasured, right? So can we go to your comparison plot between the BNL measurement, this measurement, the combination, and the latest theory published measurement?
Yeah, and I can say some words about that too.
Yeah. So so here we see now that standard model number you're showing there, that's the one that came from that consortium you mentioned earlier. Theorists. Right. Okay. Now, I think it was around the same day that yes. This result came out. Yes, there was a Nature or a Science paper that started making claims about the lattice QCD calculations.
That's exactly right.
Okay, can you comment on that at all?
Yeah, this is it. So the number that we used is what's shown here, from WP20, the white paper 20 from the Muon Theory Initiative group. Now, there are basically two approaches for getting the hydronic vacuum polarization term. One is through dispersive approaches, basically looking at this, okay? This is the vacuum polarization type of diagram we're looking at. So one way to get at this is by looking at decades and decades of high precision E+ E- experiments and basically, getting it from data-driven approach. And so the idea is you cut this diagram down the middle, and it essentially becomes this diagram, okay? Except with electrons instead of muons, okay? And so you've got E+, E-, goes to gamma, and then the gamma goes to pi+, pi-.
Yeah, but the goal is to probe that hadronic stuff at the gamma pi.
This is what we're trying to probe. And so these experiments, we've got enormous amounts of data from decades of experiments on this. The pi here is what's most important for us, okay? And so that's what's most important. And so we compare to that data, And we use the dispersion relation calculations to come up with this vacuum polarization term. Okay. Now, that has been done over many, many years. You know, over 100 theorists involved in this effort, and this is their consensus result on that. All right. Now, another approach you can use is basically just ab initio calculations using lattice QCD calculations, sort of first principles. Now, those are really, really tough to do. Now, lattice QCD has been very powerful in getting many, many different types of calculations done that are somewhat simpler than this one. A challenge for this calculation on the lattice is that it spans many scales. Okay, it spans many scales, and it's hard to connect all of that. And so it's a challenging calculation to do. There are many people that have teams that have done this, typically with very large uncertainties. The BMW 20 result, that is the one you're mentioning that was just published, it's the first one to come out with sub% uncertainties. Okay, and so you know this is a very big step forward in lattice QCD calculations. But it has not been confirmed and scrutinized and verified with other results, other techniques. And so there's a lot of work that needs to go in to confirm or refute it. And so we need the Muon G-2 theory initiative folks that include these folks, know that we've got to look at this in more detail. But it's very promising, the advances that are being made in the lattice calculation. So we'll look at that over the next few years to see how that turns out. But yeah, that's essentially what's going on. It's these two different approaches. This new one at sub% level for the first time just needs some more scrutiny and verification before it goes into the consensus view.
Okay. Yeah, Fred, I see you're unmuted. Did you want to make a comment on this?
Sorry.
So is that a no? Or are you apologizing on behalf of the entire theory community, Fred? No, I know that recently Fred had brought up some tension in these hadronic measurements and how they affect, for instance, parton distribution function fits.
Yeah.
And so I thought maybe Fred was going to raise the question of how much we actually trust those data-driven hadronic corrections in the first place, because there are interpretations that have to go from the data back to the actual theory correction for those. The whole thing is quite interesting, I think, is the bottom line.
It is. And the main thing here is that those data-driven techniques have just had a lot more history and scrutiny of them to this point. But yeah, there is definitely still more work to do on the theory side, as well as on our experimental side and nailing down those uncertainties. And one thing that I wanted to mention as well, just from a personal note, if I can find it, this is from one of the theorists that's sort of involved in our experiment, some of the implications of this result and different, possibilities, mainly that, there are sort of restricted spaces that we, can fit this into of different models. But one thing that I wanted to mention that that our experiment itself is pursuing is we're actually going to look at a couple of possibilities of physics directly. And that is that we can use our Muon G-2 data looking at our measurement of omega A over time to see, to look for if there is CPT or Lorentz invariance violating physics that could be responsible for the G-2 result. And to see if we can identify that. I mean, those are fundamental theoretical underpinnings of all that we do. But there's a big industry in checking CPT and Lorentz invariance violation. And we can do that by looking for sidereal variations in omega A, or even annual variations in the measurement of omega A. And so we're in the middle of working on those as well. And we can use very similar techniques to actually look for ultralight dark matter. And there are signatures in the time variation that couples to the mass of different dark matter candidates. So yeah, so we're looking at doing that in the future as well.
No, I think that's fantastic. And it's nice to point out, I think, as you have done here, that it's not just about inferring indirect effects using this experiment. You can go for some direct effects, that are consequences of extensions of the standard model, for example, or new symmetries or things like that. So, all right, well, I don't see any more questions, Breese. So I think on that forward-looking note, let's go ahead and end today. So let me, on behalf of the department, thank you very much for doing this on such short notice about such an exciting result. And we hope you have a wonderful evening. Thanks, Breese.
All right. Thanks a lot, guys. Appreciate it.
All right. Yeah, take care. Bye-bye, everyone.